Hello and welcome to my YouTube channel. This video we are going to talk about direct and indirect bandgap semiconductors. Till previous lecture we have seen what are bandgap, how we develop different types of semiconductors, and what is the effect of different band gaps between semiconductors. Now in this video we are going to talk about what are direct and indirect bandgap semiconductors, where these semiconductors are generally used and their applications. So first of all, let us talk about direct versus indirect bandgap semiconductors. In the previous lecture, we have seen that in general, we can have valence and conduction bands, and if these valence and conduction bands are properly aligned, that means the lowest point of the conduction band is aligned with the topmost point of the valence band, then in that case we will call such semiconductors direct bandgap semiconductors. Just for a recall, if you recall, valence bands are generally completely filled with electrons and conduction bands may be empty or may have very few electrons in them. In general, they are empty. So now when we excite these semiconductors, these electrons from valence band may go to the conduction band and they may constitute current. Now let us see what are the difference between direct bandgap and indirect bandgap semiconductors. So here on the top we have conduction band, and in the lower band we have valence band. And we have also seen the EK diagram, why it is called EK diagram, energy versus wave constant. And apart from that, we have also seen how we can develop this kind of different bandgap semiconductors. Now, the lowermost point of conduction band is called or is denoted by EC, that is energy of conduction band. The topmost point of valence band is called EV, or we can call it energy of valence band. Now, here you can see the example of direct bandgap semiconductor, because the conduction band is perfectly aligned with the valence band. Now let us see what are indirect bandgap semiconductors. So there are semiconductors in which the conduction band and valence band are not properly aligned. In that case, what happens? The electrons in the valence band, okay, if they are energized, then they may go to the conduction band. But the electrons will not directly come to the valence band when they are de-energized. We will see what does that mean in the upcoming slides. So remember, electrons from the conduction band and holes from the valence band contribute to the total current in any semiconductor device. Now let us see how these currents are basically developed and what are the different applications of these direct bandgap semiconductor and indirect bandgap semiconductors. So if we provide enough energy to the electrons which are in the valence band, then these electrons will jump to the conduction band. So if assume the band gap is given by Eg, okay, then if we provide any external energy which is greater than Eg, then these electrons will move from valence band to conduction band. Okay, so we have to provide any external energy which is greater than Eg or band gap energy. And once you remove the external energy, then these charged electrons which are in the conduction band will return back to the valence band. And because these are directly aligned, these electrons will jump back and they will generate an energy which will be equal to Eg itself, or equivalent to the band gap energy, which is given by h into mu, where h is the Planck's constant and mu represents the frequency component, or we can say frequency. So the electrons, when they release their energy, that energy will be equal to the band gap energy, and that band gap energy will be equal to h into mu. Remember, h is our Planck's constant, so that means this is a constant value. Okay, constant value, and mu is the variable, or which is frequency. Okay, so remember, when the energy is released, it is related to frequency. Okay, and that frequency may generate different light or spectrum, because remember, light is also frequency. So you have different colors of light, for example green, red, ultraviolet, and so on. And if we can design semiconductors with proper band gap, and once we energize these electrons, they will move up to the conduction band, and when the external energy is removed, then these electrons will come back to the valence band, and they will release an energy which is equal to h nu, in which h is constant, so only mu is variable. That means we can generate different colors of light using direct bandgap semiconductors. Now coming to the indirect bandgap semiconductors, in that case, the electrons which are energized and moved to the conduction band cannot directly come back to this valence band, just like direct band gap energy. Instead, they have to take a different path. In general, the electrons from the conduction band will first come to the alignment, and then they will come down to the valence band. So that means there are two different paths which are taken by the electrons in case of direct and indirect band gap. Examples of direct band gap semiconductors are gallium arsenide. In case of indirect band gap semiconductor, we have germanium and silicon. So design LEDs, we generally use direct bandgap semiconductor, provided if we can tune the energy band gap, then we can tune the frequency of the light also. Frequency of the light is nothing but different colors of light. Whereas in case of indirect bandgap energy, the electrons which are released from the conduction band back to the valence band will generate heat. Okay, so remember, direct bandgap semiconductors are generally used to generate different colors of light, whereas indirect bandgap semiconductors generally release their energy in the form of heat. Now, when we consider the movement of electron in case of indirect bandgap, the energy released is called phonon energy. Okay, whereas light is called photon. Case of indirect bandgap energy is called phonon energy. Now let us talk about direct bandgap materials. So in case of direct bandgap materials, when electrons in direct bandgap material absorb energy, they jump from valence to conduction band, and when the external energy is removed, then leaving behind a positive charge or hole in the valence band. So when you apply an external energy, so this is assume the conduction band and this is assume the valence band. So EC is here and EV is here. In that case, the electrons which jumps from valence band to the conduction band, okay, leave behind a hole. Okay, and suppose if this electron jumps to the conduction band, again this electron leaves behind a hole. So the electrons which are moved to the conduction band generates holes in the valence band, and that is called positively charged hole. Although they are neutral in nature, they don't have positive charges. Electrons have negative charges, but holes generally are neutral. They don't have any particular charge assigned to them. In direct bandgap semiconductors, when electrons and holes recombine, excess energy is often released in the form of photon, that is light. Okay, so in direct bandgap semiconductors, electrons coming back to the valence band will generate external energy, release energy in the form of photon, which is light. And by properly tuning the value of Eg, we can generate different colors of light. This property makes the direct bandgap materials favorable to design optoelectronic applications. Remember, direct bandgap semiconductors are used to design optoelectronic, that is, electronics which are related to lights, such as LEDs and lasers. Okay. Now coming to the indirect bandgap materials. So in case of indirect bandgap materials, the minimum energy required for an electron to move from valence band to conduction band involves change in momentum. Of course, you can remember, if suppose this is our valence band and here we have the conduction band, then you directly do not jump to the from valence band to the conduction band. Instead, you have to change the momentum of electron. That means the way or the path the electron follows actually has different momentums. Okay, we will come to this term momentum, why it is very essential in case of semiconductor physics. So remember, when the electrons jump in case of indirect band gap, then they involves change in momentum, and the electron cannot directly transition between the two bands while conserving both energy and momentum. So now, in case of indirect band gap, the energy released is called phonon, and which is nothing but heat in general. So phonons are quantized vibrational modes of crystal lattice in material. So definitely, if there is a vibration crystal lattice, that vibration will be generating heat, or it will be releasing heat. In case of indirect bandgap semiconductors, the electrons and holes do not have same momentum before and after recombination. So therefore, to conserve momentum, the phonon is emitted. Phonon is emitted, which is nothing but heat. Phonon is emitted or absorbed during recombination process. Both energy and momentum needs to be conserved during the transition of electrons in case of indirect bandgap materials. If the transition is perfectly vertical, then there is no change in momentum, which is in the case of direct bandgap semiconductors. But if it is not perfectly vertical, then there will be a change of momentum, which is in the case of indirect bandgap materials. Now let us talk about some terms which are associated with the energy bandgap diagram. Valleys and so valleys, that means here this is the actual diagram of the energy band diagram, whereas that we saw in the slides were very much, we can say, simplified versions. This is what actually looks like in case of actual semiconductors. So you have the band gap 1.42 electron volt, and here electrons, once they jumped from here valence band to conduction band, they will generate holes. Okay, so electrons which have moved from valence band to conduction band generates hole, and these electrons will come to the conduction band. So you may go through different such materials to understand the behavior of actual wave vector versus energy diagram. This is the example for gallium arsenide energy band diagram. Okay, so if you want to go further more in detail of this energy band diagrams, you can do some research, but this is out of scope of this presentation. So these are some of the simple examples of different semiconductors having the band gap diagrams. So here you can see the actual band diagram is between E0 and EV, or we can say EC and EV, conduction band and valence band. And these energy bands are associated with the complete lattice or arrangement of different atoms and molecules inside the semiconductor. So out of all these energy bands, we can see the closest energy band is here, and this is called the energy band gap EG, the gap between EC and EV. And similarly for different types of semiconductors, you will find different types of valleys and difference between the EG and EC. Okay. Now, these are some of the terms which are associated with the wave vectors, but these are again out of scope in the presentation. So, in general, EK diagram, using the EK diagram, we can establish lots of different behaviors or properties of any semiconductor material. For example, the average kinetic energy of electron at room temperature is given by capital E, which is more or less equal to kT. Okay, where small k is nothing but Boltzmann constant. So if k is constant, then only variable is T, which is temperature, and E, which is actually energy associated with the electron. Okay, so if you put appropriate values, so k is 1.38 into 10 to the power minus 23, and if we consider room temperature 300 degree Kelvin, and if we put the charge of electron 1.6 into 10 to the power minus 19, we will end up with energy E is equal to 0.025 electron volt. And this term is generally repeated many times when you study diodes. So there is a direct correlation between this value and the diode's current, or current which is associated with the diodes. So in room temperature, generally the germanium will have band gap of 0.67 electron volt, or in general we say 0.7 electron volt, and electrons per cubic centimeter will be 10 to the power 13. So germanium is highly packed semiconductor, whereas in case of silicon, the energy band gap is 1.1 electron volt, which is almost double to that of germanium, and the electrons per cubic centimeter is 10 to the power 10, which is 1000 times less than 10 to the power 3 times less than germanium. And in case of gallium arsenide, the energy band gap is 1.42 electron volt, and you can find 10 to the power 6 or 1 million electrons per cubic centimeter of gallium arsenide semiconductor. So here we can simplify that we have valence band full of electrons, conduction band generally totally empty. If we can provide external energy, then these electrons will move from valence band to conduction band, and when these electrons are moved, then they leave behind a vacant space, and that vacant space is called holes. This is what we study in general, that the electrons when moved from valence band to conduction band leaves holes. Remember, holes do not have any proper polarity. They are not positive in nature, but absence of electron is called hole, and in general they are considered to be positive, but they are not actually positive. So if you have any suggestions or doubts, then please share your comments and suggestions in the comment section. And with this, I would like to end the presentation. If you have not subscribed the channel, then I would request you to please subscribe the channel and share this video with your friends. If you have any doubts or suggestions, please share your doubts and comments in the comment section. Thank you and have a nice day.